Good afternoon, everyone. I hope that you can hear me. So just send me a message. Tell me if it's the audio is okay. All right, very good, Amanda. Thank you. All right, today we're going to have a presentation on construction materials. And construction materials, what we will cover today will help all of you for the morning breath exam, and also we will cover topics that will help those of you who are planning on taking the construction focus exam in the afternoon. Um, so this topic is listed on the NCEES list as they don't use the term construction materials, but they do use material properties, and they also refer to especially quality control and quality assurance. So some of the things that we will be talking about today will address those specific issues and topics that are listed on NCEES's document. And I will tell you, today I will do a complete concrete mix design for you. We will go through a complete design of concrete mixture, and that is indeed listed as a topic that will be on the test. And also asphalt materials, it's listed, and asphalt design of mixtures. I will do an example in towards the end of the presentation. So we will cover mixture design for asphalt at the end. So I need for you to be with me to actually see that. All right, let's begin here with the concept of stress and strain, and I believe you have seen this slide before, so I'm not going to dwell on it. Let's continue. And these are all related. The reason I sometimes repeat some of the slides is because I want to show you how what we cover builds upon itself. So here with the concept of stress and strain, we have, let's take a look. We have different examples, and here the very first one talks about stress and strain being or having a linear relationship. And part A, as you can see, it is a linear relationship up to a point, and that's the point where this material fractures. As you can see down here, that is glass or chalk, and those kinds of materials we talked about, that would be brittle. It would fail without any warning. So in this case, however, the material is proportional and has a linear relationship. Now let's look at part B. B, it says steel, but what you need to recognize is that up to a point, as we discussed before, has the stress strain have a linear relationship, and beyond that it's non-linear. Then part C is aluminum, and part D, this is concrete. We will spend some time on that. And also, if you recall, we talked about stress strain curves for concrete this past Tuesday. Let's move on. What you see here is, of course, theoretical, but in a few minutes I will show you exactly how this kind of concept will be tested on the exam. All right, I actually have an example problem with numbers that will show you how this kind of concept is tested on the exam. Let's start with the A. Very quickly, I don't want to spend too much time on this, but the stress-strain behavior, this is very important because what we are exhibiting here is what I refer to as plastic deformation. Let's assume that we are looking at a material where stress and strain travel along this curve, all right, along this curve up to a point, and then it's nonlinear to this point right here. Let's say this specific material, we place load on it, and the load exerts a stress, and then the material shows some type of strain, all right? And then at this point, this red cross point, let's say that we remove the load. Once we remove the load, the material returns, and this is very important that you understand, the material returns along this red dotted line, all right? And why is that? Well, because we have loaded it above its yield point. And remember, I mentioned to you before that when the load gets beyond the yield point, or the stress gets beyond the yield stress, then the material starts acting plastically, which means it will not return to its original shape. So it goes back along this dotted red line, and what is important for you to understand is down here. See what happens that the first part, let me see if I can use a different color. This green segment, that is plastic strain. That is the amount of deformation that will remain with the material. However, the balance, let me see if I can use yellow here, that we refer to as elastic strain, which is the part of strain that will be recovered. Just keep this in mind because we will use this concept in another problem. Then part B, which exhibits this kind of behavior, I'm looking at curve B. That is referred to as you can see in the bottom, elastic, perfectly plastic. Guys, don't get too excited about the nomenclature. I'll explain what that means. All right. First, elastic. We refer to the elastic part is this. It's linear up to a point. That point I call the knee point. All right? And then what happens at the knee, the stress-strain curve have a horizontal relationship, just like that. And that is, guys, that's why it's called perfectly plastic. It's plastic because it's beyond the elastic limit, but it's perfectly plastic because it's horizontal. Now, very quickly, let's cover part C. And part C, it's called elastoplastic with strain hardening. Please note, it is linear. The relationship is linear up to that knee with a certain slope. But then beyond the knee, that relationship is what? You got it. It's still linear, however, with a different slope. All right? And since the slope changes, that refers to strain hardening. In other words, it takes a less amount of y for any change in x. Just remember, elastoplastic with strain hardening, there are two segments, both linear, but they have different slopes. Okay, let's move on. And as I said, please remember this concept. I'll show you exactly how this is used, could be used on the exam. And then this is a typical stress-strain curve. We've covered this before. Here, also, again, we talked about it when I covered concrete design. So here is the fun part. Let's talk about this. Now, before I talk about what I refer to as generalized Hooke's law, what I want to do is go back and see if we can remember this concept of Hooke's law. Just want to remind you. Remember, for a ductile material, we said stress strain curve is linear up to the proportional limit. And what did I say about the slope? The slope is constant. So who can remember Hooke's law in this case? Hooke's law was E is equal to sigma over epsilon. E, which is the modulus of elasticity, which is nothing other than the slope of the linear portion of this curve, is equal to sigma over epsilon. So Hooke's law, let me see if I can write this very quickly. So Hooke's law is equal to sigma is equal to E times epsilon. So keep that in mind. But this is Hooke's law in 2 dimensions. This is Hooke's law in 2 dimensions. Now I'm going to move to slide 7. Here we're talking about generalized Hooke's law. Guys, remember, here generalized Hooke's law is nothing other than 3-dimensional Hooke's law. All right? Now, 2 dimensions would look like this. Epsilon is equal to sigma over E. Do you agree? If you cross-multiply that equation we just talked about, this is what you get. Now, that's for 2 dimensions. Here, we are extending that to 3 dimensions. Therefore, we have sigma x, sigma y, and sigma z. These 3 equations that you see, I'm going to dissect it so you will understand. If you don't mind, why don't you concentrate on this part that I just circled? Do you see the relationship? That what I circled, the segment I circled in that top equation, that is nothing other than the Hooke's law in 2 dimensions in the x direction. In other words, that's epsilon x is equal to sigma x over E. However, as you can see, that equation also has this other segment. And the other segment is minus nu times quantity sigma y plus sigma z. I will talk about this quantity nu in just a second. However, please pay attention, sigma y and sigma z happen to be the stresses in the other 2 directions that we are not including in x. All right? So, who can tell me what nu is? This is the Greek letter nu. Poisson's ratio. Helen is saying Poisson's ratio, and Helen is absolutely correct. In fact, we had a slide. I think I have a slide in this presentation also talking about it. But we had a slide last week, which I did have. It says Poisson's ratio. All right, Poisson's ratio is a constant, and it's constant for any given material, and basically it gives you a relationship between. Look, if, for example, if I come along and say that we are placing some kind of a stress in one direction, let's say we're placing stress in this direction, both top and bottom. Well, and let's say it shortens the material. Well, Poisson's ratio tells us the effect of the change in dimension along that axis. How would that affect the change in dimension normal to that? All right? So that's what the effect of nu is. Nu is Poisson's ratio, and we also sometimes use the letter mu. That's why it is in this equation, because this body is subjected to stresses from all three directions. Now, before I move to the next slide, I want you to take a look at the second equation. I just want to show you the pattern in this equation. There may be a lot of variables here, but this is not difficult. The second equation, take a look. Help me out. The second equation, look, we've got epsilon y on the left-hand side, and then on the right-hand side, we have sigma y and E in the bottom. And in the numerator, what do we have? We have nu again. Remember, this is always a negative. Negative nu times, in parentheses, we have sigma z and sigma x. Again, sigma z and sigma x are the other two stresses, because in this equation, we're looking at changes in y. So there's a pattern to these three equations. Let's go to the next slide. It talks about the Poisson's ratio. In words, you can read what that says. That's the effect that we're looking at. And nu is always equal to minus epsilon lateral over epsilon axial. Sometimes, and this is very important, sometimes there have been problems, a single problem just talking about Poisson's ratio. And what they can do is give you certain information and then say, could you please calculate the Poisson's ratio for this material? The one thing that could go wrong here, I will tell you. Please remember what epsilon represents. And I have mentioned that many times because I know it could be a problem. Epsilon is always delta L over L. So you have delta L over L in the top and delta L over L in the bottom. All right. Of course, the top is in the lateral direction, and the bottom would be in the axial direction. Now, what could go wrong, and that's when you will see a distractor, is they will plan, or they will count on you to just say delta L over delta L. Delta L in the lateral direction divided by the delta L over axial. Please don't do that. Make sure you don't forget about, to get strain, you have to divide by the original length. Now, if somebody is asking why is there a negative, that's because if you squeeze some subject or an object in one direction, it actually bulges out in the other direction perpendicular. And if you extend one object in one direction, then it gets smaller or skinnier in the other direction. So that's why you always have that negative. Now, in the very bottom line, it says Poisson's ratio of solids vary from 0.1 to 0.45. And I will tell you, Poisson's ratio for typical concrete is 0.15. 0.15 is the typical Poisson's ratio for concrete. And for asphalts, it's 0.45, which makes sense if you think about it. All right, now, here's a problem. How can they, all this theory we looked at, how is that going to be used on the test? Well, let's do this problem together. A cube of an alloy has dimensions of 3 by 3 by 3. So we have a cube, 3 dimensions. The cube is placed in a pressure vessel. This is a key term here. You need to train yourself to pick up these key terms. All right, so that's a pressure vessel. That means all sides are in compression. All right. A pressure of 3,000 psi is induced in all directions. Then it says the modulus of elasticity. Modulus of elasticity for the alloy is 15,000 psi. So take a note of that. E, modulus of elasticity for this problem, is 15,000 psi. Then they say Poisson's ratio is 0.3. So mu or nu, whichever letter you prefer, Poisson's ratio is 0.3. What they want you to do is to determine the length of each side of the cube, assuming the material remains within its elastic range. All right? So let's solve this problem. All right. What equation do we use? We use generalized Hooke's law, the three-dimensional Hooke's law. Let's take a look at the next slide. Here's the solution. What I like for you to do is make sure that you understand where each one of these numbers come from. And I will point out to you some things that could go wrong when you're solving a problem like this. Obviously, since this is a cube, and if you look at the statement of the problem, everything in the problem is symmetrical. All right? So what we need to do here, we just pick one of the three. It doesn't matter which one. One of the three generalized Hooke's law equations and just apply it. All right? So let's pick the one that gives us the strain in the x direction. So epsilon x is equal to, now, for sigma x, we used minus 3,000 psi. Why minus? Because it is indeed in compression, and I explained to you why it would be in compression, all right? So it's a pressure vessel. So, and then this 0.3 that you see, that is the that is indeed the Poisson's ratio, and it was given. Then sigma y and sigma z both are minus 3,000. All right. Now the whole thing is divided by 15,000. That is the modulus of elasticity that was also given. All right. Now I need for you to pay attention, because what we get here is what? It's epsilon. It's epsilon in the x direction. And because of symmetry, epsilon in the y direction, epsilon in the z direction, they will all be 0.08 inch per inch. Note the units. That's a strain. So delta L over L, which would be inch per inch in this case. Now, what the problem wants us to find is the dimension of each side of the cube after the pressure has taken place. Please understand that 0.08 is not the answer. 0.08 is the strain. In other words, 0.08 is delta L over L. Do you see that? So if 0.08 is delta L over L, how do we actually calculate delta L? Well, look at this equation here. 0.08 is delta L over L. Let's multiply by the original length, which is 3, and then we get 0.24. We get minus 0.24. Minus 0.24, this is delta L. This is change in length. So that's change in length. Since the cube is in compression, subtract it from 3, and this would be the answer, 2.76 inch. This is a good, very representative problem of the kind that you might see, but it also demonstrates the fact that you really have to have a good understanding that the strain really is change in the dimension divided by the original dimension. All right, let's go to the next problem. This is the strain hardening example, and it demonstrates how you might be tested on problems like this. Just a few minutes ago, we went over this kind of behavior of certain materials. Now here, they will give you some numbers, and they are asking you certain questions. So let's read this question together. An elastoplastic material with strain hardening is governed by the curve shown on the next page. Now, follow along with me. They say the modulus of elasticity is 25 million psi. Modulus of elasticity is 25 million psi. In terms of the curve, what is that? That's E, and it is the slope of the initial part of the curve. 25 million is the slope of the initial part of the curve. They say yield strength happens at 70 KSI. So yield strength is at 70 KSI. That means that knee of the curve is at y equals to 70 KSI. Make a note of that. Then it goes on to say slope of the slope of the strain hardening segment is 3 million psi. Let's take a look. 70 KSI, that's the y value of the point at the knee. The slope of this first segment is, I believe that was 25 million. And the second segment, they gave the slope of that curve. Now let's go back here and take a look. What do they want you to find? Find the strain that corresponds to a stress of 80 KSI. That's the first part of the problem. So let's just solve that. Find the strain that corresponds to a stress of 80 KSI. Shanna, I see your question. I'll get to it in just a minute. So here, remember, strain is measured on the x-axis. Stress is on the y-axis. So this is what they're asking you to do. They say, all right, for a point that has a stress of 80 KSI, the problem says, all right, what is the strain associated with that? But mathematically, what we are saying is a point on this graph that has a y value of 80 KSI, what is the corresponding x coordinate for that point? That's what we're really solving. All right? So it reduces to being able to use the slope of these different lines. And basically, tell me if you agree. If we come up with this dimension down here, wouldn't that be the answer? Of course. Let's go to the next slide and see. All right. What I would like for you to do is make sure you understand where we get these numbers. $70,000, that's the y value of the point at the knee, divided by 25 million. 25 million is the slope of this red segment. So what I just showed you gives you this dimension right here. All right? So to that, we need to add this segment. I don't know how well you can see that yellow, highlighted yellow. How can we find that? Well, let me show you. It's going to be this part of the equation. So 80,000 minus 70,000, that's the differential. And we divided it by, this is the important point, we divided it by 3 million. And 3 million is the slope of the second part of the graph. All right? If you look, when you go from 70,000 to 80,000, you're traveling on the part of the graph whose slope is 3 million. So there you go. You add that, and then you add those two components, you come up with 0.0061 inch per inch. And that would be the answer. That would be the answer. All right? The next part of this problem, they say, please calculate the permanent strain if the 80 KSI stress is removed. If the 80 KSI stress is removed, what is the permanent strain? Permanent strain is this segment right here. Right here. So somehow we need to calculate that segment, because that is the part of the deformation that will not go away. So that's the permanent strain. And this is the equation in the bottom will help you calculate that. I leave that up to you, so you can look at it yourself, make sure that you understand where that came from. However, the only thing I want to point out to you is, and this may be a question that you will raise, look here, over here, this 25 million, that is the slope of the red segment, and the reason we use it here is because that happens to be the same as the slope of this segment that you will see here. This segment here. And we use the slope of that blue line to be the same as the one in the red because they are parallel to each other. You must know this aspect to understand where this 25 million comes from. All right? So do this problem, and if you have any questions, let me know. Shanna is asking about the units of strain. Strain, think about it. Strain is delta L over L. So delta L would be in terms of inch, and L would be in terms of inch. So strain is always inch per inch, or it could be millimeters per millimeters. Sometimes there are people who say strain is unitless. You can think about it that way, but I always say inch per inch, or whatever units I'm working with. That helps me keep up. That helps me keep up with the units that I'm using. All right. I hope that helps. Okay. Now on slide number 14, this is where I'm going to start showing you a complete design of concrete mixture. I will tell you a few things before we start. I do know that some of you may work very closely with concrete. Some of you specialize in materials. And certainly structural engineers use concrete in their structural design. And if you are familiar with the mixture design of concrete, you know that many regional producers, they have their own design process. However, the exam you are about to take is a standardized national exam. So regional habits and regional behavior will not be tested or expected on the test. On the test, you will be expected to know about ACI 211, American Concrete Institute Section 211, 211. ACI 211 is the series of guidelines which are accepted, standardized, and nationally accepted as the process that we use for design of concrete mixes. Also, those of you who are familiar with this process, you know that many processes, including ACI 211, is computerized. And if somebody wants to design a concrete mixture, they usually use a computer software. However, you will not have access to a computer software or a computer on the test. Therefore, you need to learn this process. And specifically on the NCEES documents, they do mention Portland cement concrete mixture design. So that's why I cover this. However, they will not be able to give you a comprehensive question. They can't give you the kind of problem that we're going to cover and expect you to do the whole thing. But remember, every step in the process is fair game and can be a question on the test. In fact, as we go through this process, I will explain to you some of the possibilities, and also I'll share with you some of the questions that have been on the test regarding this process. So let's talk about concrete mix design. Concrete actually is a material that's made out of four main ingredients. Those ingredients are what we call coarse aggregate. This could be crushed rock of some kind, limestone or some other type of aggregate. Then fine aggregate, which is sand. And then Portland cement and water. But think about it, coarse aggregate and fine aggregate, well, this is a bunch of rocks that we put together. And it's very loose particles. We have to somehow glue these particles together. The glue is a combination of Portland cement and water. So when we combine water and Portland cement, that paste becomes a very strong glue-like material that will be binding or act as a paste glue to hold all these loose ingredients together. When we talk about the process of mix design, the process simply is the calculations that will, in the end, will give us a recipe. It will give us, for example, how many pounds of coarse aggregate, how many pounds of fine aggregate, how many pounds of Portland cement, and how much water do we need to weigh and combine together so we can get a concrete mixture with a specified strength. That's basically what the process is. And the product, what we end up with, is that recipe that tells us how much of each of those four major ingredients we have to weigh to get, for example, 4,000 psi concrete. All right, now I'm going to ask you a question. I need to consult with a structural engineer. So introduce a structural engineer to me that's among you. Just give me a city of El Paso. If you're with me, do you have a structural engineer in your group? Just give me the name of a structural engineer in any group. That's okay. We still have about an hour and a half left. I can wait. And don't worry, I will not ask any questions. Okay. Mark Taylor. All right, Mark. City of El Paso does. What is the structural engineer in El Paso? Um, okay, Elizabeth is the. Okay, so we have Elizabeth and Mark Taylor. We go with that. Mark and Elizabeth. Okay, City of El Paso, Joe Vela. Okay, Joe. All right. Let's say Joe is going to design a concrete beam. Let's say a concrete beam. Joe, give me a design compressive strength. Elizabeth, any one of you. What is a typical, yeah, 4,500. Elizabeth says 4,500 PSI. All right, let me tell you where I'm going with this. Let's say that Elizabeth is designing a concrete beam, and she decides to have a 4,500 PSI compressive strength in the mix. All right, I want everybody to pay attention. The 4,500 PSI compressive strength that Elizabeth uses in her design, that is the 4,500 PSI F prime C that we talked about in the equations when we talked on Tuesday. We talked about design of concrete beams. So the F prime C compressive strength that Elizabeth would use in her calculations is what exactly we talked about last Tuesday. Now, Elizabeth gets into a point where she will have to call a concrete producer, concrete supplier, to actually deliver that concrete to her job site. Now, this is something I want you to understand, all of you, and this is very important. When she calls to order the concrete, will she ask for 4,500 PSI? Will the concrete delivered to the job site be designed, the mixture, would that be designed to have 4,500 PSI concrete? The answer is no. The 4,500 PSI concrete, the number 4,500, she uses in her design equations. The concrete mix that you will have to order is different from that. It's this thing, which is called F prime C required. F prime C required. All right? On the test, they will ask you questions that will test this, actually. All right? So they will check to see if you understand this concept. So F prime C required, that would be the compressive strength of the mixture that we will have to actually come up with. That would be the compressive strength of the concrete that's delivered to the job site. The 4,500 that Elizabeth uses goes in here in the equation. We have to, based on ACI, we have to calculate both of these values. We have to use both of these equations, come up with F prime C required, and whichever is larger will control. All right. What is, in this equation, what's S? Who can tell me, who could guess what S might be? Standard deviation. Mary is telling me S is standard deviation, so is Amanda and Donald. You're correct. S stands for the standard deviation, and the standard deviation actually is a measure of quality control of the concrete producer, the company that actually you're buying the concrete from would have a standard deviation, and the smaller the standard deviation, that represents better quality control. If the standard deviation is large, and I'll give you some example. If the standard deviation of a concrete producer is about 300 psi, for example, that's pretty good. If the standard deviation is 1,000, that means things are pretty loosey-goosey at that plant. All right? So anyway, I will demonstrate the use of this equation later. And by the way, the city of El Paso gave me 3,500 psi as a typical value. So that's good too. It doesn't really matter based on the member. Okay, so this is a normal distribution. And by the way, if anybody, you may not be wondering about this, but if anybody in that equation was wondering about where do we get the 1.34 times the standard deviation, statistically, if we are that far away from the mean value, that means we have the probability, 90% probability, that's 100 minus 10, 90% probability that we will get what the structural engineer needs. All right, does everybody get that? For example, if Elizabeth specifies 4,500 psi in her design equations, then if we use this one of those equations that I just showed you to come up with F prime C required, then we have it will be a larger number than 4,500, but on the average, we have a 90% chance that we will get what she needs in her structural design expectation. The concept of standard deviation, sometimes they actually give you problems that requires you to calculate the standard deviation. In other words, they give you a series of numbers and they say, what's the standard deviation of this? Well, on this page, tag this page, this simply tells you how to calculate that. And some calculators will help you do that automatically anyway, so know how to do it. Sometimes this has shown up on the test. So let's move on. Here we have the very bottom line is important. This equation is used if the concrete supplier has 30 consecutive test records. What they're referring to here as equation is are those two equations that I just showed you. Remember the two equations that give you the F prime C required on the left-hand side? Well, those equations are valid as long as the S, the standard deviation that you use, the standard deviation for a supplier would have to be based on 30 consecutive test records. That means 30 different mixes that they make. They come up with a standard deviation based on 30 consecutive tests. If they don't have 30 tests, this is the table that you need to use. I need for you to tag this page also. Sometimes this is a very simple question, but it lends itself to multiple choice type questions. All right? What if a concrete supplier does not have enough data to calculate its standard deviation based on 30 consecutive tests? What if he only has, let's say, 25 tests? All right? Well, if that's the case, you take the standard deviation that he calculates based on 25 tests and multiply it by a factor, in this case 1.03. All right? Now, if the test, if this S value is based on 20 tests, then you multiply the standard deviation that he calculates based on, multiply by 1.08, and if it's 15, you can see that 1.16. Now, I have been asked before, can you interpolate with this table? The answer is no, you cannot. For example, if a supplier has tests based on, let's say, 22 consecutive trials, then the factor that you use would be this thing, 1.08. So if it's based on 22, you would use the one for 20, and so on. All right? Let's move on. Every concrete supplier, they actually do have a standard deviation. Whether they share it, they choose to share it with us or not, that's a different story. But they do have a standard deviation. However, let's say that there's a producer that just does not give you the standard deviation, or you are, if let's say you are away from, if you're away um, the location of the concrete supplier. All right. Let's say your company is in Kansas City and you're designing something, some remote area. All right. What happens there is ACI, and they tell you, you have no idea what their standard deviation is. Well, then this is what you use. And GEI is asking, what happens if S is based on less than 15 tests? Well, this is exactly what you do on page 20, slide 20. If the standard deviation is based on less than 15, you do not use it, and this is the method that you will have to do. All right? So here, if the concrete that you're designing has a strength less than 3,000 psi, then what you will have to do is add 1,000 to it, which means you will order a concrete mix that has 4,000 psi strength. So what we are saying, Elizabeth used 3,000 psi in her design equations, in design formula, designed the beam based on 3,000 psi, but since there is no standard deviation available, she would just add 1,000 psi when she orders the concrete. So she orders 4,000 psi in this case. Now, if the concrete is between, if the compressive strength is between 3,000 and 5,000, ACI says in the absence of a valid standard deviation, you just add 1,200 to it. So you order, let's say if it's 4,000, you order 5,200 psi concrete, and so on. You can see if it's over 5,000, you add 1,400. Guys, let me tell you, here we're just looking at numbers, and this is perfectly correct if you have an opportunity to use this on the test. But look, if you only need 3,000 psi and you're forced to design to order 4,000 psi, that's a lot of money. That would add a lot of money to your project. All right. Ryan is asking, is the standard deviation an F prime C value? It's not an F prime C value, but it carries the same F prime C units. I think that's what you're really asking. So yes, the standard deviation would be is in terms of PSI. All right. Here's a problem that I would like for all of us to do. All right. So let's look at this problem together. We have, if somebody calls you and asks you to please do a concrete mix design for me, before you can perform the calculations, you must have certain information. The first thing that you need to know is, what are you going to use this concrete for? All right. So type of construction. What are you going to be using this for? All right. In this case, it's a reinforced concrete footing. So we're using this concrete that we're going to, you and I are going to design together right now. It's going to be used for a concrete footing. Then you need to know about the exposure. What we mean here is exposure to the elements. In other words, is it something that's going to be inside in an enclosed area, or is it going to be something outside? Or is it going to be a structure that's going to be in contact with water? All right? So that's all important. In this particular example problem, we say exposure is mild, and they say it's below ground and not exposed to freeze-thaw cycles or sulfate water. Um, Freeze-thaw cycles, this is really important because if the specification is that the location or the type of structure will be exposed to repeated freeze-thaw cycles, then we will make a decision to make the concrete more durable by using air entrainment. Air entrainment is used to increase durability in terms of increased resistance to freeze-thaw cycles. I will talk about air entrainment in a few minutes when we do the solution. Then you also need to know the maximum size of aggregate. Maximum size of aggregate, in this case, they say 1.5 inch. In the U.S., it's customary that we use what is available locally to minimize the cost of hauling or transporting the aggregate. So that's why sometimes we just see what's available locally and see if we can use it for the project. However, there are cases where they don't give you the maximum size aggregate like this one. And they will give you a series of requirements and parameters, and on the test, they will ask you what should the maximum size aggregate be. This kind of question has shown up on the test several times. And I will specifically tell you what you need to know in order to answer those questions. Next, you need to know the slump. And in this case, the slump is 3 to 4 inches. I will explain to you in just a second what slump means and how we measure it. But please remember, it is a measure of how fluid the concrete is. And it's also an indication of the workability of concrete. Then you also need to know the compressive strength. In this case, it's 3,500 psi. And this is the specified 28-day compressive strength. Always when we talk about F'(C), the compressive strength of concrete, I mentioned this before, we're talking about what the concrete strength is going to be in 28 days after inception, after we mix it. All right? But remember, this 3,500 psi is what Joe in El Paso or Elizabeth use in their actual structural design. All right? And we need to convert this to what we called F'(C) required with those equations that I showed you. Okay. Before you start the process of design, you need to know certain characteristics about the materials that you will be using. In this particular case, we're going to use cement type 1 cement. And the fine aggregate, the sand that we use, has these properties. The bulk specific gravity is given, bulk density is given, fineness modulus is given, and very, very important, the moisture condition. The same thing we need to know about the coarse aggregate. Those same quantities we know. All right, and I will show you in just a minute, well, when we go through the solution, exactly how you use these numbers. But I want to point out something here. Fineness modulus. Fineness modulus is an index that shows us how fine an aggregate is. Either you could use it for fine aggregate, for sand, and also for gravel, for example. But the reason I pointed out is that fineness modulus, this concept, shows up on the test quite a bit. In fact, one recent exam had two or three questions on the same exam about fineness modulus. We will talk about that today. All right. Now, remember I told you we are covering ACI 211. ACI 211 specifies these 8 steps. All right. So when we go through the mixture design, these are the 8 steps that we have to follow. I'm not going to read these to you. However, I want you to tag this page. If you could tag this page, because as we go through this process, I'm going to follow exactly these steps. All right. So we need to keep track of where we are. But we're going to do exactly what each step says in the order specified. I want to tell you, number 8 is really important. The last item, it says adjustment for water content may be required. But look, with big emphasis, I'm saying will be required. That adjustment for water is so important that it will be required. And I'll show you exactly how you do that. But again, it's so important by itself. It has shown up on the test, and it can. This slide here, slide number 24, this is actually recently I added this slide to the presentation because this kind of questions just showed up on the test not too long ago. And it's possible they will ask you this. Now, if you know this concept, it's not difficult. But if you don't know it, well, you just don't know it. Guys, I tell you, there are 5 types of cements, Portland cement. There are 5 general types, and very creatively, we call those type 1, type 2, type 3, type 4, and type 5. What you need to know for the test is the differences between each one, and also what they like to ask you is they want to know if you can match the type of cement to specify in a certain condition. All right, so let's talk about it. Type 1, and I need your help with this. Type 1 basically is the what we call normal, and this is the kind that is used for the majority of everyday concrete structures. Type 2 is called moderate sulfate resistant. So a cement that's produced and sold as type 2, that cement gives us some moderate resistance against sulfates compared to normal. All right? So type 2 compared to normal has some moderate resistance against sulfate. Most general type cements that are used and sold these days, however, is a combination type 1, type 2, and they sell it as type 1/2. Now, let's talk about type 3. Type 3 is important. It's called high early strength. If Elizabeth or Joe, if they use or specify high early strength cement, type 3 cement, in their for their structure, this is the kind of cement that reaches very early on a high strength, which means within probably a week or so. All right? Or it could be even sooner than that. All right, so early on, it achieves a high strength value. It does it by generating a lot of heat. And this is basically what happens. When cement and water, they come contact with each other, when you add water to cement, there is a chemical process. It's called the process of hydration. And the process of hydration generates a lot of heat, which we refer to as the heat of hydration. When we use cement type 3 or high early strength in the structure, when it comes to in contact with water, it actually gives off a lot of heat. It gives off a lot of heat early on during the process. So I'll ask you, what situation would you specify high early strength? Give me some idea. When would you need a high level of heat generated? David is saying cold weather. Absolutely. Mary says high traffic areas. Well, I think what she's referring to is being able to open to traffic soon. All right. So, and El Paso is telling me high traffic streets as well. All right, guys, let me tell you, high early strength, you use high early strength if you're doing accelerated construction. In other words, as several of you mentioned, if you want to, for example, open the road to traffic early, you use high early strength. But something else that David said very early on, cold weather. If you're using in cold climates or cold weather, high early strength is what you need so you can gain strength early on, and that heat of hydration that's generated will offset the cold. All right. Yeah, ACM Chicago, I see your question. I'll get to it in just a minute. Now, let's talk about type 4. Type 4 is low heat of hydration. What you need to understand, they will give you, for example, they just say type 4, and they expect you to know what type 4 the name is. Type 4 relates to low heat of hydration. All right, so when we use this type of cement, when it comes to contact with water, it generates much less heat of hydration. It does not generate a lot of heat, lower than, of course, normal or type 1. Remember, all of these properties are measured against type 1. All right? So tell me, when do you think you would use low heat of hydration or type 4? Give me some ideas. Elizabeth is saying mass concrete. Absolutely, mass concrete and gravity structures, large masses of concrete. But Mary Hill is saying hot weather. Yeah, hot weather, and David says hot weather. That's one of the main reasons you would use low heat of hydration. If it is during summer times, or if it is in Texas, for example, when it's hot weather, so you can benefit from that low heat of hydration. Let me tell you, and also mass concrete, for example, a dam, or when you have a large quantity of concrete that will be placed in a enclosed area. Again, a dam would be a good example of that. Low heat of hydration will be very helpful. So type 4 would be used for that. But let me also tell you one other reason for using type 4, which we have not, which I don't think anybody mentioned. Listen, if there is a distance between where the concrete is produced and the construction site, all right? So if you have to haul this concrete in its plastic form for some distance, all right, that is when you use type 4, because the low heat of hydration will prevent the concrete from hardening during this transportation process. So for example, if the construction site is some distance away from the plant, sometimes, of course, you can, if it's a very, very large job, you set up the plant right there where the construction site is. But if that's not possible, low heat of hydration, type 4 would be helpful. All right, now let's talk about the last one, and then we'll move on. Type 5 is called high sulfur resistant. This type of cement will give you resistance to sulfate, and somebody asked me what we meant. A couple of you asked me, what do we mean by type 2 when we said moderate sulfate resistant? Well, allow me to answer that when I'm talking about type 5. When we talk about type 5, that is high sulfate resistant. Where would you specify this? Well, I'll tell you. One thing, if it is a structure that is going to be exposed to water for a long time, or for sometimes for the entire service life. For example, ports. When you have harbor structures, think about it. They're exposed to constant water and salty water, or the type of, there are some sulfate in the water which will, or sewers, gravity sewers. Jeremy says gravity sewer for type 2, but type 5 also will give you resistance to high sulfate. Freeze-thaw, for example, if you have repeated freeze-thaw cycles, type 5 will help you with that. If you have a structure, concrete structure, that's going to be exposed to corrosive chemicals, high sulfate resistant, type 5 is what you specify. All right? And then type 2, Jeremy says gravity sewer manholes, but think about type 2 to use in situations where you have the structure exposed to the same things I talked about in type 5, but it is not as severe. Not as severe. All right, let's move on. Okay, remember the slide that I told you? There are steps 1 through 5. Well, step number 1 for the mixed design. Step 1, if you go back to that page, I don't remember the page number. Helen, tell me what page number was that specified the steps. 23, thank you. So 23, page 23 says step 1 is the slump. So in this case, it's given to be 3 to 4 inches. Now, there are cases where they don't give you exactly what the slump should be. They ask you to specify it. All right? And I'll show you how that's done. Here is the slump. This is, many of you, all of you may have seen this, but basically what we do, we have a standardized slump, a cone, which is 12 inches high, and we place it in the cone, we remove the cone, and then let the concrete slump. And we measure how much the concrete actually slumps, and that would be this measure right here. So whatever that is, we call the slump of that concrete. And think about it. The overall dimension is 12 inches. So if the concrete, let's say slump is 11 inches, which means it's very, very soupy. So that means it slumps all the way down here, so it's very, very soupy. However, um, most slumps that we use within 3 or 4 inches, that's what the consistency that we want. But it's really slump is not a measure of quality. We have to use it for, match it with the specified method of placement. Now, remember I told you, if they don't tell you what the slump should be, this is how you decide. All right? What they can do on the test, they give you a certain parameters like this, and they say, well, what would you specify as a slump? Let's assume that they say reinforced foundation wall and footings. That's what you're designing. Well, based on ACI table 5.31, they say the slump maximum is 3, minimum is 1. By the way, we don't just use one number. We use a range. In this case, 1 to 3 inches of slump would be specified based on table 5.3.1. Now, by the way, these table numbers, they are the actual table numbers from ACI 211. All right? They may ask you mass concrete. What slump would you use for, or specify for mass concrete? Minimum of 1, maximum of 2. This is how this works. All right? Now, step number 2, and this is, guys, this is very, very important. Step number 2 on page 23, it refers to the size of aggregate. In this particular problem, they say 1.5 inch. What if they don't give it to you? And many questions have been on the test asking this. All right? So this is very important. How do you decide what the maximum aggregate size is? Well, the maximum size of the aggregate should not exceed these 4 conditions. 1/5 the narrowest dimension of a concrete member, or 3/4 of the clear spacing between reinforcing bars. Circle this clear spacing. It's not center to center. Clear spacing between reinforcing bars. 3/4 of that. Number 3, 1/3 of the depth of a slab. And the last one, 3/4 of the rebar cover. 3/4 of the rebar cover. Let's move on to the next slide. I know people learn in different ways. Some of you feel more comfortable looking at words. Some of you look at sketches. So we have both. This slide 29, in a sketch form, I'm showing you exactly what I showed you on the previous slide in words. All right? As I told you, this has been on the test before. Very recently, by the way, one of the questions was this. They were asking what should be the limit based on the clear spacing between 2 rebars. So the aggregate size should not exceed, which means should be less or equal to 3/4 of the clear spacing between the rebars, D. And what they were, the answer was this, 3/4. All right? Guys, any one of these could be the one that is on the test. Okay. Now let me tell you, Amgad, Fahmi, I'm not following what you're saying. Could you check that? Um, let me tell you how they do it. One way to ask you a question about this is, as I told you, the 3/4, 1/5, 1/3. That could be the criteria they're asking you. However, they could also give you the part of a drawing. They could give you a sketch of a, let's say, a column connected to a beam, and they give you different dimensions, including the dimension of the connection and the dimension of the slab. And they ask you to decide what the maximum aggregate size should be. In a case like that, guys, what you need to do is pay attention to all these four criteria simultaneously and apply all that apply to that are included in that drawing. All right? And of course, when you apply 2 or 3 of these, the number that controls would be what? Would be the smallest. So the maximum aggregate size acceptable would be the smallest of the 2 or 3 that you calculate. Basically, let me tell you, the reason for all this is so the aggregate would be small enough that would freely flow between the rebars and not get clogged between the rebars. All right, so what I just told you is very, very important. Pay attention to it. All right, let's move on. Step number 3 is mixing water content. In this case, we want to know, remember the recipe that we're designing, how much water do we need? All right, so in order to decide that, we're going to consult this table. That's table 5.3.3 of ACI 211. All right, there are a lot of numbers in this table. One thing I want you to pay attention to is that this table actually is in 2 separate sections. That's one. So the top section you use if you're designing non-air entrained concrete. And then there is a bottom section to it, as you can see. And you specify or you concentrate on that part of the table if you're designing an air entrained concrete. First of all, when do you choose to design air entrained versus non-air entrained? I think I did allude to this. I mentioned this earlier. When we looked at the statement of this problem, this goes to exposure. In this particular case, they said exposure is mild. So if the exposure is mild, if we are not concerned about freeze-thaw cycles, then what we're going to design is non-air entrained concrete. So in this particular problem, we're going to concentrate and use the top part of the table. All right. However, if exposure was severe, then you would use air entrained concrete, the bottom part. All right. Now let's see how we can use this table. First of all, now that we know it's non-air entrained concrete we're designing, let's look at the slump. The slump for this particular case, they told us 3 to 4 inches. All right, so that's the column that we need. What about the maximum aggregate size? Maximum aggregate size is 1.5 here. All right, so this is what we do. Extend the horizontal line here, vertical, and this is the number that we read, 300. All right, so what we need in this case is 300. So 300, what is that? Read on the very top of this table. 300 is the mixing water, how much mixing water we need in pounds, 300 pounds. All right? This table also give us what's known as air content requirement. This air content, this is the type of air that we cannot prevent from having. It happens It occurs because of the mixing action. When we mix the aggregates in the drum, and other operations that we do, there is some level of air that's introduced into the mix. And we need to identify that. In this case, this is how you decide. Based on the maximum aggregate size, you just come all the way down here and you pick that number. So that's 1%. So 1% is the approximate amount of entrapped air in non-air entrained concrete. Please note the word entrapped. This is entrapped air, and it's not the good kind air. The kind that's good is air entrained, all right? But entrapped air, just remember, in this particular mix, it will be 1%. So we go back to page 30, slide 30, step 3, mixing water. Here's the answer, 300 pounds. And I just explained to you how we got that. And then approximate amount of entrapped air is 1%. I also told you how we got that one. Let's move on to the next slide. All right, here we are all the way to step number 4. And step number 4 has to do with compressive strength. And here you're going to help me find the F prime C required. We have spent some time looking at those two equations. And in this particular case, they specify the standard deviation S in this equation to be 300 psi. So 300 psi is the standard deviation we're going to use. Ryan, bigger. All right, so let's calculate this. So what do we use for F prime C? In this particular case, Elizabeth or Joe, what would they use? Well, this problem said 3,500 psi. All right, so let's substitute 3,500 psi for F prime C, 300 for S. The first equation gives us 3,900 psi. Substitute in the second equation, we get 3,700 psi. So which one, guys, which one controls? The largest one. All right, so you calculate both of these and the largest controls. So in this case, even though Elizabeth or Joe used 3,500 psi in their design of the beam, when they order the concrete, they need to order concrete that's 3,900 psi. All right, so that's what we have to do the mix design for. So the compressive strength is a function of the water to cement ratio. Write that down. The compressive strength is affected highly by the water to cement ratio, the ratio of how much water we have in the mix versus how much cement we have in the mix. All right? So in order to achieve 3,900 psi, we need to use this table 534A to see what the water to cement ratio should be in the mix design process. All right, now the problem is we said 3,900 psi, and there is no 3,900 psi listed. We have 4,000, we have 3,000, but not 3,900. What will you do? Interpolate. In this case, you can indeed interpolate, and you should interpolate. But let me tell you guys, if this was an actual situation that I was doing the design, if I needed 3,900 psi, I would just use 4,000. All right? But the test, the exam you're preparing for is not a practical exam. It's a highly theoretical exam. Therefore, we need to interpolate between 4,000 and 3,000. Basically, since we're doing non-air entrained, if it were 4,000, it would have been 0.57. If it were 3,000, it would be 0.68. So we need 3,900, so it'll be somewhere in between, but as you can see, it will be very close to 0.57. And here it is. On slide number 36, water to cement ratio is 0.58. All right, so we're going to use 0.58. That's after we interpolate. All right, now let's move on. At this point, we know the water to cement ratio is 0.58. So if that is the case, remember from a previous step, we calculated 300 pounds. We said 300 pounds of water we needed. So this is very simple. If you know how much water we need, you need the water to cement ratio is 0.58, then very, very simple operation. How much cement we need is 517 pounds. I hope that you can follow that. So the cement content is 517 pounds. Now, before we do this one, I want to go back. This is slide 34, and we already looked at this. This is slide 34. We looked at it, and this table gives you, there's something important I want to point out to you. This table gives you the water to cement ratio based on strength. All right? Well, there is one other element that we need to check, and that is the durability of concrete. All right? Sometimes, look in the bottom of this table, it's the durability of concrete in service. Sometimes it's not the strength that controls, it's the durability requirements that control. For example, I mentioned earlier, if you design for example, a harbor, a port structure that's exposed to water its entire time and service life. Well, it's not so much the strength that you worry about, but durability, resistance to that chemicals in that water is what you should worry about. Sometimes sewer lines in very harsh environments. All right? So, in a case like this, what you need to do is also, in addition to the previous, see here, it gave us 0.58 based on strength. Here, we're looking at durability requirements. So what you have to do is read this section and these columns and match. If they give something to you like this on the test, you see those column headings, read those and match whichever is the best match for you for the problem. And let's assume that this is where we are. Let's assume that this is where we are. Based on durability, or 5.34b, this table, let's assume the water to cement ratio that's specified is 0.5. Everybody with me? So let's say we specify 0.5 based on durability. Based on strength, this table, we came up with 0.58. So which one would control? Tell me. Strength says water to cement ratio 0.58. Durability says water to cement ratio of 0.5. Which one would you choose? Let me see if anybody is asking, telling me. Yeah. Stephen Arash says pick the durability. Blake, Stephen, many of you are saying choose the 0.5. Absolutely. All right. So this is what I want you to decide. the less water, think about this, the less water we have in the concrete mix, the more durable that concrete will be. All right? Therefore, if it's between 0.5 and 0.58, we go with 0.50. All right? Um, and if you have excessive amount of water in the mix, more than what the design required, what happens is when that water shrinks, then you get shrinkage cracks, and also additional water will increase the water to cement ratio. Therefore, that higher water to cement ratio decreases the strength. And that is one reason why civil engineers, structural engineers, materials engineers, they really get upset when people in the field, they just start indiscriminately adding water to the load, to the concrete. Because what it does, it increases the water to cement ratio, and it decreases the compressive strength. Also, it lowers the durability of that concrete. All right. Step number 6. Step number 6, this is where we are going to basically calculate the volume of gravel, how much coarse aggregate we need. And in order to explain these numbers, I need to take you to the next slide. Slide 38 talks about table 5.36, talks about how much coarse aggregate we need. And let me show you how this slide works. On this column, the column on the left, let's identify the maximum aggregate size that we are using. In this case, the maximum aggregate size is 1.5. All right? Then these, on the right side, the 4 columns, these numbers here, what do you think those are? You got it. That's the fineness modulus of sand. So this is the fineness modulus of sand. We have 4 choices, 2.4, 2.6, 2.8, and 3.0. Remember, guys, earlier I told you that the fineness modulus is a factor, is a parameter we use in the mix design, but for some reason it's very popular on the exam. All right? So in this case, help me out. What is the fineness modulus for the sand that we are using? Mary, maybe you can look it up, or Helen, or Joe in El Paso. By the way, El Paso is one of my favorite cities. So here, 2.8. Yeah, okay, thank you. Many of you are telling me Matt said 2.8. So in this particular case, it's specified that the fineness modulus of the aggregate is 2.8. All right, so come across with 1.5 inch. Down here, according to the fineness modulus, the number we get from the table is 0.71. All right, so the number we get from this table is 0.71. What I need for you to understand is, what is that 0.71? What does this represent? Take a look up here. It says the 0.71 is the volume of dry rotted coarse aggregate per unit of volume of concrete. All right? So the volume of the coarse aggregate that we need in this mix is 0.71. Does everybody follow that? So the volume of the coarse aggregate is 0.71 per unit volume of concrete. What does that second part mean? Well, remember, ACI 211, this design process that we are using, this actually, the ingredients and the recipe that we come up with, and that recipe will give us 1 cubic yard. Remember that. Write that down. So we are going to get 1 cubic yard of concrete using this ACI process. So I'm going to go back to the previous slide. So that's where the 0.71 comes from, and then that is the dry rotted volume of gravel. But note what I did here. I don't want anybody to get confused. The 0.71, we just got it from the table. Then we multiply that by 27. What do you think that is? Yeah, 27 is a conversion factor. We go from 1 cubic yard to 27 feet, 27 cubic feet. All right? Yeah, Paul is saying cubic feet per yard, and Jeremy also. So make a note of that 27, and then that comes out to be 19.17 cubic feet. So this is how much volume of aggregate, of gravel we need, 19.17 cubic feet. All right? But that's in volume. What would that be in weight? Because that's easier to work with. Well, we take that 19.17 and multiply by this 100. I really get nervous when I cover this. This 100, we don't multiply it by 100 because it's a nice round number. We multiply by 100 because this is a certain characteristics of the gravel that's specified on the page, which gives us the characteristics. Donald says slide 22. Thank you, Donald. So if you go to slide number 22, William says it's the bulk density. Make a note of it. We multiply the volume by the bulk density of the gravel in this case. And that just happened in this case to be 100. So we multiply by 100 for that reason. And then, by the way, for the exam, be prepared to know how to go from volume to weight and vice versa, because not only for concrete, but when you deal with soil, that comes up also. All right. So at this point, it's 1917 pounds weight of the gravel, and Stephen says it's dry rotted weight, not bulk density. That's correct. All right, now, this table we've already looked at. Let's move on to slide 39. Slide 39, remember I told you fineness modulus shows up on the test. Here is the equation that gives you what fineness modulus is, and or how it can be calculated. A couple of things I want to point out. Fineness modulus for fine aggregate, for sand, for example, ranges between 0 and 6. All right, so remember that. Fineness modulus, it's nothing other than just an index that tells us how fine the aggregate is. So for sand, it's between 0 and 6. For coarse aggregate, for larger aggregates, that range is between 0 and 9. And exactly how you calculate it, this is the equation. And you may say, well, you know, this equation is, what's the big deal? Well, let me tell you what the big deal is. Please note, not only we have a summation, but we have cumulative. So make sure that you understand, if you have an opportunity to apply this equation, it's the summation of the cumulative percentage retained by weight, the whole thing divided by 100. Now I'm going to show you an example. There is no significance to the frog. So on page 40 we have this is an example. And what you can see, they will give you, on the test, they will give you these two the columns on the left. All right? They will give you these numbers that are in these two columns on the left, and they ask you to please calculate the fineness modulus. So you create this third column and the fourth column, and that's the cumulative percentage retained by weight. Happens to be 293 divided by 100. Fineness modulus for this case, it's 2.93. Go over this example problem and find others similar to it. You can appreciate how it's done. All right, it's not difficult, but understand how it's done. By the way, the fineness modulus, as I said, is just the measure of fineness, and it has nothing to do with the gradation of the aggregate. You have a session on soil mechanics or geomechanics, and you will look at the distribution of the grains and gradation of the of soil. In this case, and I don't want to spend much time on this at all, but those of you who are geotechnical engineers and the rest of you will see this better after we cover geomechanics for you. But look, there are three different samples: this yellow, purple, or cyan, or whatever that thing is, and this blue. These three curves show clearly three different gradations for these three aggregates. However, look at it. For all of those three, the fineness modulus is 3.00. So fineness modulus has nothing to do with the gradation of the aggregate. Let's move on. Page 43, this summarizes steps number 1 through 6 of the mix design. This is a repeat of what we have done, but clearly specified in one slide. We have summarized what we have done so far. Next, step number 7. We're getting close to the end. Step number 7, this is where we calculate how much sand we need. And let me explain here. Basically, we're going to use what I call the absolute volume method. With the absolute volume method, this is what you need to do. Remember I told you the volume of the mix that we are calculating a recipe for is 1 cubic yard. 1 cubic yard or 27 cubic feet. All right? So at this time, we know how much water we need, how much cement, how much gravel, and how much sand is what we're calculating right now. So this is what we are going to do. We're going to convert, for example, in terms of water, convert the 300 pounds to its equivalent volume, cubic feet. We divided that by 62.4. You know where that comes from. All right? So in this container, we have 4.81 cubic feet of it is water. Then convert the cement to its equivalent volume. It's 2.64 cubic feet. And again, 196, we got that from the given information. Volume of gravel is 11.43, so this is how much gravel it takes up. But then, remember air? We said entrapped air of 1%. Pay attention to how we got it. 1%, 0.01 times 27, this is in cubic feet, gives you 0.27 cubic feet. So let's also decide how much air takes up. The balance is going to be how much we need, how much sand we need to complete 27 cubic feet in this container. So all we have to do, look down here, please. Total is 27. 19.15. 19.15, by the way, guys, if you add all of that, you come up with 19.15. So the red section is 19.15. The blue is going to be the balance, which is 7.85 cubic feet. What this means is we need 7.85 cubic feet of sand. Converted to weight, weight of sand is 1272 pounds. All right? So right now we have the recipe. Let's look at page 45. So what we need to create 1 cubic yard is this much cement, this much sand, this much gravel, this much water. And that will give us 1 cubic yard. Guys, the next step for the design actually is to take this recipe that we've come up with right now, take it to a lab and do what we call a trial batch. All right? We do a trial batch to see how close we are to these properties that we are designing for. But 1 cubic yard of concrete is a lot of concrete. So what we knew, it's customary that we divide it by 100. We divide everything by 100, so instead of 1 cubic yard, we have 1/100th of a cubic yard in the lab, and that is manageable. So this step is very important, guys, because this is where I tell you how to do a moisture correction. And this is so critical that it really created some of the concrete producers that don't pay attention to this step. They have gotten in a lot of trouble. All right, and also on the test, this is so important. You will see it on its own could be a question. So cement, the actual cement is highly controlled. So we don't need to worry about moisture correction for the cement. If you really need a moisture correction for your cement, you have bigger problems than this. However, let's look at the sand. How much sand we need? Well, the calculation so far says 12.72. However, that is based on SSD. Who can tell me what SSD stands for? Absolutely. Saturated surface dry. Yes. Saturated surface dry. So here we have the sand. Go back to the original statement of the problem where the characteristics of the sand was given. They told us it is wet, and they gave us a percentage. What was that percentage? I believe the percentage was 2.5%. Right? Yeah, 2.5%. Jason and Fami are saying 2.5%. Okay, let me show you how that 2.5, how we use that. The 2.5%, that's in terms of percentage, but that's going to be 0.025. All right? So that's 0.025. 2.5% is equal to 0.025. So multiply 0.025 by 12.72, and that gives me 0.3. This 0.3 is the moisture correction. So to correct the amount of sand, what I need to do is add the 0.3 to the 2.72. Pay attention what I'm doing. I'm adding the correction factor to 12.72, so the actual amount that I need to mix is 13.02. Now, you may ask, why did I add it? Well, I will explain, and we don't have a whole lot of time for me to repeat it, so I'll just explain this once. Guys, our calculations based on saturated surface dry condition requires 12.72 pounds of sand. So in the final mix, we need to have 12.72 cubic, 12.72 pounds of sand. But this sand we're using is wet. In other words, it's going to bring in 0.3 pounds of water. So think about it. 0.3 pounds of that sand that we are measuring is going to be water. So in order to end up with 12.72 pounds of solid sand in the mix, how much of this wet sand do we need to weigh and add to the mix? It would be 13.02. All right? The rule is this. If it is too wet, add the correction factor. If it is too dry, subtract the correction factor. All right, now let's take a look at the next item, which is correction for gravel. Correction for gravel, for the trial batch, we need 19.17 pounds. What is the moisture condition? They said it's wet with 0.5%, 0.5% wet. All right. So So this is 19.27. So this is 0.5% is 0.005. Multiply that by 19.17, and that gives you the correction factor of 0.1. So it's too wet, so you add 0.1 to 19.17. All right, so you end up with 19.27. Jeremy is asking what slide shows the 2.5%. If somebody looks that up and tell me. 22. Amanda says 22. Jeremy, it's on page 22. Thank you, guys. And Amjad is asking. He thinks that we used 0.5 water to cement rather than 0.58. No, we did not. We are still using 0.58. The 0.5 that I used was just in case, not this problem, but some other problem if durability was an issue. Okay. And sand, yes, sand can be too dry. Sand can be too dry, yes. All right, so, okay, let's get back to this. At this point, we need to calculate how much water we need to weigh and add to this mix. Now, the big point here, and this is really a big issue here, because, guys, since both sand and the gravel are, in this case, on the wet side, each one will bring some water into the mix. The sand brings in 0.3 pounds of water, which becomes part of the mix, and the gravel brings in 0.1 pounds of water. So we need to account for that. So here's what we do. When we're looking at the water, we said we need 3 pounds, but 0.4, the total of 0.4 comes from the aggregate. So what do? We subtract the 0.4, and the amount of water that we actually need to weigh and add to this mix is 2.6. Does everybody see how this works? All right. Now, one self-test is the following, and this is also helpful because as I'm showing here, the total addition of all the ingredients before the moisture correction should equal the total weight after the correction has taken place. So that is a self-check. Step number 9, forget about this. In order to do step number 9, you really have to have access to an actual laboratory, and highly doubt if you will have access to that. I just realized we are almost out of time. Here's what I'm going to do. If you guys don't mind, I'm going to use 5 more minutes. We're going to use 5 more minutes because I need to cover this. Asphalt concrete, the next few minutes I will show you how you can design an asphalt mixture. And here there's only one method that we will use. And the method that we will use is called performance grading. These other methods of grades of asphalt binders, penetration, viscosity, and viscosity of age. These are traditional methods, but I would say from 10 to 12 years ago, we started the process of new performance grading. And if you get a question on the test, performance grading is what you will see. This slide I'm not going to go over. This is just basically shows a flow chart where asphalt oil comes from. It's from the process of hydration. Process of refining crude oil. So performance grading, PG grading. Some of you who work for a state agency, you probably are familiar with this, but It's not a very difficult concept. Let's take a look. PG grading, an example of it is like this. PG 58 minus 34. That's an asphalt binder. All right? The way you specify it is PG 58 minus 34. Let's look at what those numbers mean. PG stands for performance grading. The first number, 58, guys, the 58 is the largest temperature that this binder, this asphalt, is designed to be exposed to in terms of Celsius. And then the second number, which is minus 34, is designed, this is the lowest temperature in Celsius that the binder is supposed to get exposed to. Now, the binders are standard. So we have specific standard performance grading binders. Guys, I know there are a lot of numbers here. Don't worry about it. What I want you to concentrate on are these very top. All right? These are, and I will go over this with you, these are the standard grades. For example, PG 46 minus 34, PG 46 minus 40, PG 46 minus 46, or PG 58 minus 16, and so on. I explained to you what each number means. However, what you see on this page and the next page, these are the only standard binders that are available to us. There's nothing else. One thing I want to point out to you, and this is important that you note, everything is increments of 6 degrees. For example, from 46 to 52, that's 6. 52 to 58, the difference is 6. And also, the difference of 6 is true with the negative. So 22 to 28, 34 to 40. Just remember that. Why is this? Well, the engineers and scientists who came up with this process, that's the decision that they made. All right? Now, here is a problem. If you get a question like this, about this, this is how you will get it. They say, consider the following condition. The average 7-day maximum pavement temperature in some location, the average 7-day maximum pavement temperature is 56 degrees centigrade, and the standard deviation is 22 degrees centigrade. Then they say, also the average 1-day minimum pavement temperature. The average 1-day minimum pavement temperature is negative 23 degrees centigrade. All right, that's the 1-day coldest day. And then the standard deviation is 4 degrees centigrade. This is given. What they ask you to do is this. What PG asphalt binder will you specify to result in 50% reliability? To result in 50% reliability. That's problem 1. And problem 2 says, what PG binder will you specify to result in 98% reliability? Guys, this is only these two are available. All right, there's nothing in between. You either design 50% or 98% reliability. Obviously, the 98% reliability will cost a whole lot more. All right, so let me show you how this is not difficult, so stay with me for a couple of minutes. I'll show you. If you want 50% reliability, this is what you do. You will take, on this same page, look at 56 degrees centigrade. On the high side, 56 degrees is the average 7-day maximum. So that is going to be the first number. Look at the top part of this slide. You see this 56? That's where I got the 56. Does everybody see that? 56 was given as the average of 7 days of high temperatures for that location. So that 56 becomes the mean value. So here's the answer that we have to work towards. So you specify PG56. PG56. And what about on the low side? Help me out. The low side, if you go back to the previous slide, they say 1 day average coldest, or not the average, 1 day coldest is minus 23. That's where we got the minus 23 here. Now, help me. Mary, if you go back to those standard mixes, do you see a mix? Those 2 pages of standard mix. Is there a PG56? No. All right. Then there is no standard PG56. So what do we use? So in order to get protection for 56 degrees, where would you go? Which one would you use on the high side? 58. Jeremy says 58. Okay, I accept that. Is there a PG58 minus 23? Is there a 58 minus 23? No. Kenneth says no. So what would you use instead of minus 23? Arash says minus 28. Some other of you say minus 22. Guys, minus 28 is correct. All right? And the minus 22 would definitely be a distractor here. But think about it. The answer here is PG58 minus 28. The problem, what can go wrong is you think minus 23 is what you need, and you may just pick 22, and that would be wrong. Think about it. This is on the negative side. If you need protection for minus 23, you will not get it at minus 22. You have to go all the way to minus 28. So there it is. The answer for 50% reliability in this case would be PG58 minus 28. All right. Very quickly, I want to show you for 98% reliability. For 98% reliability, what do we do? In order to get 98% reliability, we need to move away from the mean 2 standard deviations. All right? So we're going to move away from the mean 2 standard deviations. So tell me, on the hot side, what was the standard deviation? I think they gave you 2 degrees. 2 centigrades was the standard deviation. So 2 times 2 is 4. And look, that's how we got to 60. So move away from the mean 2 standard deviations, therefore we get 60. What we're doing is we're designing PG for 98% reliability. So the first number is 60. Let me see if I can change this. So the first number is 60. What about the second number? Well, the second number, again, 2 standard deviation away from minus 23. This is the cold side. We have to go away to get the severe side. So here, they give you 4 degrees centigrade as the standard deviation. So 2 times 4 is 8. You move away 2 standard deviations, what do you get? You get minus 31. Does everybody see that? Minus 31. So statistically, 2 standard deviation away from the mean will give you 98% reliability. Once again, Mary, do we have PG60? We do not have a PG60. So what do we use? Well, in order to get 60, El Paso, standard deviation for the cold side was 4 degrees centigrade. Oh, you're asking why multiply by 2? Statistically, that is the way it works. That's the statistical method. Just accept it. All right? To get 98%, it's 2 standard deviation away. For PG60, we don't have it, so the closest one would be PG64. Does everybody agree? And then do we have a minus 31? No. To get minus 31 protection, where do we go? Minus 34. So there it is. For 98% reliability, we would use PG64 minus 34. All right? So PG64 minus 34 would be the 98% reliability, and 58 minus 28 is 50%. Guys, this is the method that you use to design a binder. Now, example 2 for SuperPave. This process is called SuperPave when we work with PG or performance grading. This problem is similar to the last one. I leave it up to you. Please solve this as an example, and the solution is right here. If you have any questions, let me know. By the way, before I leave, I want to point out to you this top reference. This is one that I would highly recommend for the kinds of problems that I covered today. If you can get hold of that document, it's published by Portland Cement Association. It's called Design and Control of Concrete Mixtures. Very, very helpful. And it has a lot of the materials that I covered today. Guys, I'm out of time. Look, the next 2 weeks, yes, Mary, an older version is fine. The next 2 weeks, my colleagues will be working with you. We'll cover hydraulics, hydrology, and also a very important session dealing with environmental issues and waste and wastewater. And those of you who are taking water and environment in the afternoon, the next 3 sessions are very, very important. And also, all of you, for the morning breath exam, the next 3 sessions, my colleagues will be with you. I will come back and be with you exactly 2 weeks from now, and we'll do geometric design. I will miss you the next couple of weeks. Stay safe, stay warm.